Thanks for coming. We're going to talk about lazy evaluations, and we're going to talk about how it's useful. Just to quickly set the stage, we're going to talk about laziness in a couple of different languages. I'll show just a little bit of Haskell, a little bit of Scala, and then we'll jump over to Java and look at some other things. But a quick show of hands, how many of you are lazy? Excellent, I'm in the right place, absolutely. So laziness actually is pretty darn good, isn't it? Because laziness means it's efficiency. And that's what I want to talk about today, is to see how laziness can lead to efficiency. Best time to ask questions or make comments is when you have it, so please don't hesitate or wait till the end. Anytime is a great time, just draw my attention, ask your questions. I'll be more than happy to listen to what you have to say. So let's talk about what does it really mean by laziness? Well, it really turns out to be that our objective here is to defer evaluation, postpone evaluation. Now, why do we really want to postpone evaluation? Well, the saying is that if you really want something efficient, or you want to do in the more efficient way, you can never beat it by just not doing it at all. That's probably one of the best efficient way to do it, is just avoid doing things you don't have to do. So the question really is, if you want to really perform computations efficiently, what if we can find those computations that really don't have to be done and completely discard them? Then we can use the resources, spend time on doing things that are absolutely necessary. That's what we're going to look at today, how we can do this, but more so, how these things are built into languages that we actually use. I want to start with something that's pretty fundamental in computer science, but unfortunately we could program for a good 20, 30 years like I've done, and maybe never even experience these things because the languages we use predominantly, the so-called mainstream languages, sometimes don't just support certain features. And as a result, we don't get to experience certain things that are pretty wonderful in our field. So I want to talk about applicative order versus normal order. Well, it's kind of funny because the word normal order is pretty abnormal. Not many languages actually do this. Well, most languages in the mainstream actually use what's called the applicative order. The word applicative order, think of the word application or invocation of a function. Functions are evaluated when you apply them or when you invoke them rather than doing them later. A normal order, on the other hand, is where its execution is deferred. Let's take a look at this really quickly to see how this would actually work. So I'm going to start with a very little example right here. This is an example in Haskell where I'm going to write a function called add a and b is returning a plus b. So a very simple example of an add function. Well, in Haskell, functions are pure by default. They don't have any side effects, and that plays a very important role in these kind of decisions. Then I'm going to write a method called evaluate, and the evaluate method takes a value and simply returns a value. And then I implement a main method, and in the main function, I'm going to simply print, and what I'm going to print here is the result of evaluate. I'm going to call add with 1 and 2 and ask it to evaluate that little call. You can see that Haskell reported a 3, not a big deal. Everybody understands this code, so it's exactly what you would expect. But what's really interesting in this code, though, is if you go to Haskell and say, hey, Haskell, I want you to call add, and Haskell would say, why? Well, because I want to send it to evaluate. And Haskell says, then go call evaluate. Okay, Haskell, run evaluate. It says, but why? Because I want to pass it to print, and print has a side effect. It's going to display the result. And Haskell says, well, then go call print. Don't waste my time calling stuff you don't really need to call right now. Of course, we know that add actually was called in this example. How do we know that? Because we did see the result of 3. That's a proof that add was actually called. But I really want to prove that add was actually called. Well, unfortunately, though, what do we do normally in languages like Java and all the other languages? Let's be very honest about it. The world-renowned debugging technique ever is print, isn't it? We all do this, right? We don't tell in public we do it, but we always do it. And that's exactly what I wanted to do, go print a print. And Haskell got very angry at me. It said, what are you trying to do? You're trying to put an impurity in a function that's supposed to be pure. I couldn't do it. So I was kind of stumbled on it. I said, I want to prove to myself before I prove to anybody else. And I never thought I would use a debugger to prove anything in my life. And in this case, what I decided to do was exactly that. I'm going to run the GHCI, which is the REPL for Haskell. I'm going to load this program we have on our hand, which is the sample.hs. And now that I've loaded it, I'm going to put a breakpoint, and I'm going to put a breakpoint on line number 1, and I'm going to put the breakpoint in character number whatever that character is, character 16, let's say, and then I'm going to ask it to execute the main function at this point. When I execute the main, you notice the code is breaking right there on line number 1. Between 1 and 15, it's breaking. Now I tell Haskell to continue, as you can see here, and you can see that the result is 3. So I took the pain to prove what is pretty obvious, which is the add function is being called. We were breaking right inside of that. But on the other hand, I go back to this code, and I'm going to return a value of 42 right here. When I execute the code, you notice the result is 42. Once again, you go to Haskell and say, Haskell, call add. And Haskell says, but why? Because I want to send it to evaluate. It says, well, then go call evaluate, don't bother me. Okay, call evaluate. It says, but why? Because I want to send it to print. Well, then go call print, don't waste my time. So now we call print, and within print it calls evaluate. Within evaluate, it simply returns a 42, discarding the value itself. So calling the add method would be complete waste of performance and effort. Why bother calling it? So when I run this code, I'm going to tell you that add was never called. And of course, the question is, prove it. So let's go back here and run the REPL one more time. Let's load the program one more time. Let's set the breakpoint again on line number 1, character number 16. But this time, let's go ahead and call the main function. And notice it never really stopped within the add method. That shows us that Haskell was absolutely lazy. So in other words, Haskell says there's no real point in calling methods until we really know that the methods you are calling is going to be actually used. In this case, add is not going to be used at all. Why bother really calling it? That's deferred evaluation baked into the language. Well, I'm going to say some languages are born lazy. On the other hand, some languages have to work really hard to be lazy. It's kind of like me. I'm always hyperactive, trying to do something. And my wife will tell me, why don't you relax? I was like, how do you do that? And that's really hard for some of us because we're always hyperactive. Well, in some languages, you really work hard to become lazy. Let's think about this a little bit as an example. How do we really evaluate things eagerly versus lazily? It would be really nice if it becomes a semantical way of doing things in languages, because lazy evaluations gives us really good performance, because lazy evaluation simply means we can postpone evaluating something until we no longer can evaluate it. Now, what is the benefit of postponing things? Well, if we postpone something, either we never do it, or we do it only as much as necessary, but more important, we do it when we absolutely have to do it. So right now we can focus our time and effort doing something more important, and that's basically what laziness is. Remember the time, I know this is a little hard, but remember the time when you were in school. Did you really study for the exams throughout the semesters? No. The ones who study for exam every single day, we call them losers, right? But instead, what did you do? You said, there's an exam on the 15th, I will study for it on the 14th. Because you know very well, a lot of things can change before the 15th. The weather could turn really bad, who knows it? The teacher may die. There's possibilities like this that could happen, isn't it? So what do? You just wait until the 14th, and then you say, this is inevitable right now. Let me just study minimally to get the grades. Honestly, has anybody ever asked you for your grade in your entire life after you graduated? So the whole process is just bizarre, isn't it? Well, we get through it, we're pretty efficient, and we survive really well. Exactly the point. Okay, I'm just kidding, but only a little though. But the point really is that we really want to be efficient in what we do, and so we want our computation to be efficient as well. Well, how do we really make efficiency in other languages? Let's look back a little bit differently. I'm going to write a method called compute, and where the compute method, this is Scala, and in the compute method, I'm going to simply say return the given value. Not very exciting. But within this, I'm going to simply call called over here, so we can print out the fact this method was actually called. Well, that's our little Scala code right there, as you can see. And what I'm going to do here is to say value x is equal to, let's say 4. But I'm going to say if x is greater than 4, and x is greater than 5, and compute of x is greater than, let's say, 7, then I'm going to say, we'll just simply say, for example, path 1. On the other hand, if it is not the case, I'm going to output, in this case, print line will say path 2. Well, here's a little simple code, assuming I don't have any compilation errors in this code, assume that. Well, my question to you is, when I execute this code, will compute be called? What do you think? I'll give you a clue. The answer is either yes or no. What do you think? Will compute be called? No, of course not. What's the reason compute won't be called? I heard somebody say that, the S word, short-circuiting, right? Well, everyone knows about short-circuiting. In fact, mothers feed their children and they teach them about short-circuiting when they're young, saying when you grow up, become a programmer, you should know about short-circuiting, they tell them, right? Because short-circuiting is something we all know. In every language that's worth using, it uses short-circuiting. Well, the person who introduced short-circuiting was actually John McCarthy. He introduced this as part of the Lisp language, and every language ever since has been doing this, and we call this as short-circuiting. So when I execute this little code, what you see as an output right here is just path 2. So there is no doubt about it in our minds. I'm going to switch over really quickly to Java just for a second. I'm going to say public static int compute, and I'm going to say this is the number n that I'm receiving, return the value n. When in this case, of course, I'm going to output, let's say, called over here. And very much so, I'm going to say x is equal to 4. And then, of course, if x is greater than 5 and the compute of x is greater than 7, pretty much writing the exact same code. In this case, in Java, I'm going to say path 1. Otherwise, I'm going to say else output, and I'm going to say path 2. And clearly in Java, it didn't really call the method also. So we all can celebrate short-circuiting. Every single language does that. On the other hand, I'm going to go back to this code and say, well, let's take this away and put it as temp right here. Now I'm going to say val temp is equal to compute. Question for you, will compute be called now? Yes, I hear yes. Let me change my question. Should compute be called now? No. What a waste, isn't it? You know very well compute shouldn't be called, and yet compute is called by the language. What a sad story. Does anyone know why Scala calls compute right now? Because it didn't a few minutes ago, right? Well, the reason is Scala says, what if the compute method has a side effect? What if you're writing to a database? What if you're writing to a log file? What if you're performing a transaction? My gosh, if I don't call it, you'll be upset. You said, wait. Just a second ago, it was the same function, and you didn't call it. Why? Because everyone knows about short-circuiting. Well, the point really is, notice the injustice here, isn't it? On one hand, it didn't call it because we know about short-circuiting. On the other hand, it calls because it's not a short-circuiting. What if you're afraid that it's going to have a side effect? Well, this is one of the benefits languages like Haskell has. Because in languages like Haskell, a function is pure by the birth of the function. This is what I call as safe defaults versus unsafe defaults. Language like Java, Haskell has safe defaults. Language like Java has unsafe defaults. In Haskell, everything is pure. In Java, you have to beg for things to be pure. So it's pretty opposite spectrum of things, and Haskell can optimize a lot of things. Language like Scala says, what if you had a side effect? Well, it really comes down to language spec, if you will. So if I go back to Java here, notice I take this compute out of here, put the word temp again like we saw a minute ago. I say temp is equal to compute, run the code in Java, and sure enough, Java called it as well. On the other hand, you're back here in Scala, and in Scala I'm saying, but Scala, come on, we really know between you and me, we're not using this value. I don't have any side effect that's really important. Why don't you skip calling it? Well, that's so many words, you can say it by using the word lazy. So by saying lazy right here in Scala, when I execute the code, notice it did not call that actually at all. Well, as you can see here, without the word lazy, it is executing the compute method, but with the word lazy, it is not calling the compute method. But of course, if I set the value of x is 14, you can see that it is calling the compute method, but when the value is not greater than 5, it's not calling the compute method. So this becomes part of the language where you are able to say, hey, I want you to know that if you don't really have to execute it, just delay this, be lazy about it. Isn't that pretty cool to be able to do that? Let's try that here in Java. I'm going to go back here and say lazy right here and ask it to execute it. But it doesn't work. For a minute there, you said to yourself, oh my gosh, isn't it? Sorry I did that to you. Okay, so sorry, that's not quite the case. Java doesn't have that feature. But you know one thing about programmers, right? Nobody stops a programmer. The programmer says, who says no, and rolls up the sleeve and says, let me show you how to do this. Well, we're going to create laziness here in Java. How do we create laziness? I'm going to say hands down, in computer science, this is the best word ever spoken. I have to be honest about it. I am almost in tears when I say this because there's not a single day I ever program when I don't pause and thank this guy for his wise words. His name is David Wheeler, and David Wheeler said something that is probably the most profound thing ever said in our field. And he said, in computer science, we can solve almost any problem by using one more level of indirection. This is absolutely indirection. So this is probably one of the most profound words ever spoken in our field, I think. And why is this so important? Because what it says is, if you don't know how to solve something, go solve something else in turn that will in turn solve that original problem. By using level of indirection, we can solve almost any problem. And to me, call me silly, but it takes me time to learn things. It takes me time to understand things. And when I learn things eventually, I just stand up and say, oh my gosh, I finally get this. That's what excites me. The candies don't excite me. Toys don't excite me. These concepts excite me. And what really excited me was a realization when I had one day, and suddenly it dawned on me, and I was screaming almost saying, oh my gosh, lambdas are a level of indirection. And to me, this changed my way of thinking because lambdas are a level of indirection in our programming paradigm. This is an amazing design tool we have on our hand now. So what is a lambda? Well, think of an apple for a minute. Not the computer apple, but a fruit apple. Suppose I take an apple. I use the gentleman over here. If I were to give him an apple, he's got 4 options on his hand. He could be really hungry right now. He could eat the apple right away. That's like eager evaluation of the apple. Or he could say, you know what, I'm going to eat it after the topic is over. Maybe I'll eat it during the break. That's a lazy evaluation of the apple. Or he could say, I'm going to give it to the lady next to me. I don't really want it right now. He could pass this on to somebody else, much like you could pass on a lambda to some other function. Or he could just throw it in the trash and discard it. So there are 4 options when an apple is given or a lambda is given. You can call it right away, you can call it later, you can pass it around, or you can totally discard it. Well, that gives us the ability to do a deferred evaluation. Instead of calling a function right away, put the function into a lambda. The lambda is evaluated right now, but the lambda is not executed at the moment. So lambdas automatically give us a level of indirection, and that becomes a very powerful design tool on our hands. Let's take a look at how that actually works with a little example here in the case of Java. Let's say bye to Scala right here, switch over to Java. So what I'm going to do here in the case of Java is, notice this line number 11, we are immediately calling the method compute. That's applicative order right there. We're applying the function compute, immediately calling it. But instead we are saying, hey, you know what, let's not really eagerly call the compute method. Let's postpone it to a later time. So how do we really do that? Well, in order to do this, I'm going to bring in the functional interfaces over here. And what I'm going to say in this case is, I'm going to say int right here, but instead I'm going to say supplier. And this is supplier of, let's say, integer. And I'm going to call it temp is equal to. Notice, rather than calling the compute method, we are introducing beautifully a level of indirection. That here, right there, is the level of indirection that you see right there. That is how simple it is to add a level of indirection into the code by saying, don't call compute, instead pass the compute to the lambda, and then hold on to that lambda for a minute. Now that we create a supplier of temp and put the lambda in there, then we can come here and say get right here, and then when we execute the code, you can see we did not bother calling the compute method. Now, of course, there's a deficiency in this approach. We can solve problems later on, but it at least gives us a glimmer of hope that we can actually head in this direction. If you really want to do this, well, you could write this all by yourself if you wanted to. Nothing stops you from doing it. So what I could do is I could potentially take this a little further, and I can say, well, the problem in this code is if I were to call temp one more time and call the get method, it would re-evaluate the function. What if I don't want to reevaluate the function? What if I wanted to cache the result and reuse the result it was already evaluating? That would be really nice, isn't it? One way to achieve that would be to say class, for example, and I can create a class called lazyT, and within this class lazy, I could provide a constructor, for example, where I can take a supplier of this particular object, and I can say the supplier, and then I can continue in this regard, and I can provide a class like this. And about 10 minutes of effort later, you would have your own lazy class implemented. And the minute you finish implementing it, one of your colleagues will come to you and tell you, good job, by the way, that's not thread safe. And you're going to spend another 15 minutes on this code. Or you can say, maybe I'll use a library to do this. And one such library is called the Project Lombok. Project Lombok gives you annotations to do exactly the same thing, so you can mark it with the @lazy and be done with it. So these are things we can explore. The point I'm getting to is not that we want to do these things, but the point is that knowing that these things are possible gives us a lot of design tools on our hand, and we can start exploring some of these ideas. But I want to take this idea a little further with something else that we need to really focus on, which is that laziness can be extremely powerful and very useful. Well, like I mentioned, laziness comes through lambda expressions, but I want to talk about laziness just a little bit even further. Let's be careful about the tools that we use. When it comes to programming, we want to really make use of very elegant and effective tools. Let's talk about imperative style of programming for a minute. Let's talk about imperative style where, let's say, I want to take a collection of numbers 1 to 10, and I want to find the total of, let's say, a double of even numbers. So how would I do this in the imperative style of programming? Well, in the imperative style of programming, you would say int total is equal to 0. You want to output the total when you are done with it. And then you say for int I, well, okay, that's really nasty. We'll do this way. Numbers, and then I'm going to say if element mod 2 is equal to 0, well, I got an even number, then total plus equal to the element times 2, and I can do the product of that. This is called the imperative style of programming. What do we do in imperative style? You tell what to do and also how to do it. Has anyone written code like this before? Yeah, of course, right? Some of you raised the hand, others are just grieving, so they don't want to raise the hand. I fully understand that. But more important question is, how do you feel when you write code like this? Really dirty. That's how you feel, right? You go home at the end of a very long work day, the children come running towards you, say, don't touch me, I gotta go shower first. That's how you feel about it, right? That's the kind of code, a high ceremony code we are writing. That is a very high ceremony. So I'm going to say, first of all, imperative code, imperative code has high ceremony. And also, not only that we have a ceremony on it, and has accidental complexity. So this is one of the things we have to really deal with, is that it has the accidental complexity baked into it. But on the other hand, functional style code is less complex and is less ceremonious as well. Let's write this exact code in a functional style and see how it feels. We're going to say in this case over here, numbers.stream. What in the world is a stream? A stream really is an internal iterator. Then we put the iteration on autopilot. Then we say filter in this case. And then we say given an element mod 2 is equal to 0, give me only the even numbers. Map to int, given an element, double the values for me. And then when you're done with it, perform the sum operation on the value. When I execute this code, as you can see, the output is exactly the same of this code as the previous one as well. However, notice the code in the bottom. The code begins to read like the problem statement. You do one pass through the code. I have a little challenge for you. Walk up to a programmer, give them an imperative style code, and ask them to read it. But you sit in front of them and watch their eyeball movement. The imperative code, their eyes go like this, up and down, and then it does this. That's called the point of confusion, right? They're like, I don't know what's happening here. Whereas here, you are reading it top down. Given all the numbers, get me even numbers, get me the double of them, total it, let's go home now. So it becomes really easy to understand the code. It does not have the accidental complexity in the code. However, we have to be extremely careful with what we are doing. Because one of the things to be careful about is, what do you talk about? When you look at this code, what can you say? We can say the code is cute. It is definitely cute, isn't it? You look at this and say, oh my goodness, the code is cute. It's expressive. But I'm going to make a claim here because I know this for sure. I'm going to say cuteness is not sustainable. This is true. Cuteness is not sustainable. And why is that? This is the life of humans. Human cuteness lasts for 2 years. When you have a little baby, what do you say first thing? Oh, how cute. Wait until the baby is 3 years old. We don't respond that way anymore. You're talking too much. Why don't you be quiet for a few minutes, right? So the cuteness lasts for 2 years. That's all it is. So cuteness is not sustainable. We cannot simply say, the code is cute, we should be happy about it. Because about 2 weeks later, we're going to be asked the question, what about performance? And honestly, when Java said they're going to introduce lambdas, I did not care. And the reason I did not care is I said, I've done lambdas in a lot of different languages. Why do I care that Java has lambdas? And honestly, I discarded it. I said, I don't care about it. And if you ever listen to one of my videos back in time, I was that guy on the other side of the picket line constantly complaining that Java sucks. And then one day, this was about 2.5 years before the release of Java, I was just browsing through in denial saying, I don't think I need this. I don't think I need it. And then I stumbled on the streams, and I literally stood up and said, oh my goodness, this is amazing. I wrote the first book on Java 8, released on the day that Java 8 was released, but one of the things I wrote in the book was something I truly believe in. Of course, some people call me and ask me, why do you write such thing in a technical book? I always tell them, because I live in Colorado. They fully understand what I mean when you hear this. I tell them that lambdas are the gateway drug, but streams are the real addiction. And the point really is, it kind of hooks you in. You kind of get drawn into it by looking at lambdas, and you say, my God, this is really interesting. But what really hooks you in is the streams API. It did that for me. And the point really is, the streams are amazing. Why? Because when you look at a lot of different languages on the other platforms, Ruby and Groovy and JavaScript and Python and so many other languages, they give you the cuteness of the code, but they do not give you the laziness of the evaluation. And to me, the cuteness without the lazy evaluation, expressive code without lazy evaluation, simply doesn't cut it. And the reason is, we use languages like Java on very large enterprise applications. We cannot simply throw features together and say, isn't that beautiful, isn't that expressive, let's go home. No, we are not going to go home because performance matters at the end of the day. So to answer this question, let's take a slightly different example and play with it. Let's go back to this example where I'm going to take a list of numbers, 1, 2, 3, but notice I said 5, 4, and of course 6, 7, and so on. I switched the order. But this time I want to say, find the double of the first number greater than 3 and is even. So how do we write this code in the imperative style of coding? Well, in the imperative style, I'm going to first of all say int result is equal to 0. Then I'm going to output the result when I'm done with it. But within this, I say for int element coming from numbers, then what do? If element is greater than 3 and I say element mod 2 is equal to 0, then what am I going to do? I'm going to say result plus is equal to element times 2. Well, is this correct? And I'm sure you're looking at this and saying, no, this is not correct. I am responsible to make sure I break out of this code. If I don't put the break, my result is either, in the best case, inefficient. In the worst case, it's actually incorrect. So we write this code, and then we execute it. It gave us the result of 8. But the question I'm going to ask you is the result correct one more time? And initially you may say, yeah, it looks like it's correct. But the problem really is, what happens when the testers get a hand on it? I always get these words from my tester. My tester comes to me and says, hey, Venkat, your code sucks. I always tell my tester, don't say that. Tell me how my code sucks today. Because every day it sucks differently. And the point really is, this code is broken because my tester tried with a collection of numbers which are empty, a collection with no even numbers, a collection with even numbers less than 3. And it's broken on at least 3 counts. He still keeps on going with it. The point really is that this code is hiding a lot of details. Let's write this code in the functional style. How do we do this? I'm going to say numbers.stream right here. But in this case, I'm going to say .filter, given an element greater than 3, and then I say filter given an element mod 2 is equal to 0. Then I say map given an element times 2. Then I say find the first. And I ask for the very first element in the collection. Well, what does it return to us? It returns an optional. So I can then say or else and make a conscious decision to return a 0 if that's what I wanted, if the value doesn't exist. But if you notice again, the code here is very highly expressive. It is beautiful. It's easy to understand, easy to maintain. It is cohesive. How is it cohesive? Cohesion is where a piece of code does one thing and one thing really well. Every single line of code is doing exactly one thing here. Like my fingers together here. I can remove one if I wanted to, or insert one if I really wanted to. It becomes really easy to modify the code in the functional style, whereas it can become a dysfunctional mess very quickly by maintaining that code. But the question again comes back to the P word, what about performance? So to answer that question, let's go back and throw something together right here. I'm going to say is GT over here and pass the element E. I'm going to go take this one and say is even and pass the element. I'll change this to double it and then pass the element to this also. Let's see how it's going to work together. Now I'm going to write the function public static, let's say, over here. And in this case, of course, I'm going to say Boolean is greater than, and I'm going to pass the number, let's say n over here. And all I'm going to do is return n over here is greater than 3. Likewise, I'm going to implement the other two methods here as well. Here's the is even, which is simply going to return n mod 2 is equal to 0. And finally, this is going to return an int. I'll call this as double it. And this is going to simply return an n times 2. And we are going to execute the code. And what does this really provide for us? If n is greater than 3, if n mod 2 is equal to 0, then we want to return a double of the value that we are using over here. So in this case, of course, if greater than 3 is of e is equal to true and is even, then we are executing it. But the question is, what's the performance? Let's focus on the imperative style code first. Remember, we have the values 1, 2, 3, 5, and then 4. So is 1 greater than 3? No, short circuit. 2, no. 3, no. 5, yes. But 5 is even, no. And then we check for 4, check for even, check for greater than 3, double it. That's 8 computations. Is that really true? Well, we can prove that very quickly. I can go back to the code here and say, is greater than 3 called for, and then we will say plus n. Similarly, we will go ahead and put that here for the other two as well. This is even, and finally double it. So when I execute the imperative style code, let's forget the functional style code just for a few minutes right now. Let's just stick with the imperative style code. You can see the output from this code is exactly what you just saw, which is it's calling those 8 different calls. Notice it examined 1, 2, 3, 5, and then 4, but it never touched anything after 4, like 6, 7, and 8, and we call that efficiency. But that efficiency came with a price. We had to work extra hard. That efficiency comes with a price. The code is hard to maintain. The code is hard to work with. Now the question is, what's going to happen to the functional style code? Make no mistake, not all languages are created the same. In a lot of different languages that provide the functional style of programming, this will result in a pretty inefficient code for a large collection. Those would go off and create a one collection given, it'll create a second collection, a third collection, a fourth collection. and then only to discard everything and take the first value. How would you feel if somebody did that to you? You worked all night long and they say, good job, I won the first one, you can throw everything else. You're like, are you serious now? And this is okay if you have a small set of values, but for a large set of values, this is not going to cut it. But that's the way a lot of languages work because they don't focus on efficiency. I'm not complaining about those languages, I'm just making an observation. But when it comes to languages, you want not just the beauty, not just the elegance, not just the expressiveness, not just the cuteness, you want performance as well. How does that work then? This is what I learned about streams, and it just blew my mind. And what I found out was streams share a characteristics are only found among my own children. I have teenagers at home. If you have teenagers, you know what I'm talking about. If you don't have teenagers, remember the time when you were that teenager, you know what I'm talking about. Teenagers are fundamentally lazy. They don't do any stuff usually. I'll tell you what I've seen at my home. My wonderful wife will tell my son, hey, turn off the TV. It's like no words were spoken. The TV is still on. Then she says, throw the trash out. Not a muscle was moved. Then she says to him, do your homework. Not a pencil was picked. Then she says, I'm calling daddy, and everything works. This is exactly how streams work. They could have renamed this as call daddy or call mommy, depending on what you want to call it, right? Call a parent. So the point really is, this becomes the terminal method of execution. And the minute you see this method, here's how streams work. When you go to a stream and say, filter, another day. Hey, filter again, some other time. Map, maybe. Find first, oh dear. Let's get this done. So let's understand how this actually works in this context. What is important to keep in mind is a stream does not execute a function for every object in the collection. Instead, it executes a collection of functions for every object, but only as needed. So let me emphasize this. Stream is not a collection of objects. It is a collection of functions. That's what it really is. So one of the beautiful things about streams really is, stream does not evaluate a function for every single object. It doesn't do it. I want you to look at line number 10 for a minute. Look at line 10. It doesn't execute line 10 alone for every single object. Instead it says, I'm going to take line 10, 11, and 12 and fuse them together. And once it fuses it, that becomes a collection of functions. And then it says, I'm going to execute that collection of function for every single object, but only as necessary. Let's see if this is true with a little example here. So let's get back to this code and say sample, and we will call is greater than. Similarly, we'll go back to this code right here and say this is going to be sample and is even. And finally, we'll go back to this code and say this is sample, and we will call this as double it. Now when I execute the code, what's the output this code produces? It is identical to what the other piece of code did, which is the imperative style of code. So in other words, it started processing 1, and then 2, and then 3, and then 5, and then 4, but it never touched anything after 6 because the find first said, let's go home, we are done, we have the result on our hand. That is lazy evaluations. So lazy evaluations are extremely important for us to honor because without laziness, we are not going to really get performance, and this becomes absolutely critical. I'm actually using lambdas pretty extensively on very large applications. We literally have millions of lambdas in our applications at runtime. And yet, I'll be honest about it, I go to work every day with fear. What if the performance is not going to be? And that's exactly the word to use. That's called fear. But in reality, though, we're not getting any performance degradation at all for the reasons that lambdas are efficiently implemented, but more also that we really have the lazy evaluations in place. So given this, where can we go from this? Well, there are two things we can really have to look at. One of the things is, for laziness to be really practical, we need to be sure that we are honoring immutability. And this is extremely critical. I want to give you a very quick example of this before we go further about immutability. So let's take a little example of numbers 1 to 3, if you will. And in this case, I'm going to simply say that I will take this particular code and say that I want to use a value. So numbers.stream, and I'll say .map, given an element times 2. But I'm going to store this away into a stream right here. So I'm going to say right here stream, and I'll save this here as of integer. And in this case, I'll say stream is equal to. So we saved it away as a stream. Then what am I going to do? Then I'm going to say over here stream.forEach and system.out, and we will just print it, println. Now in this example, I'm using a stream, as you can see. So this is the stream API. When I run the code, this is going to give us 2, 4, and 6. Well, what is this that we are dealing with right here? This is lambda. Lambdas are stateless. This is something important to keep in mind. Lambdas are stateless. Lambdas do not carry a state. They take an input, they give you an output, they are done, they go home. On the other hand, if I modify this code to a .map, where I take an element e times factor, what in the world is factor right now? Well, a factor is going to be something I defined right here. Final int factor is equal to 2. When I run the code, it produces the same result. But what is this? This is called a closure. Why is it called a closure? Well, closures close over their defining scope. When you're alone in a room, try doing this. Say the word close over several times, over and over and over. It kind of says like closure. That's why it's called a closure, because it closes over. But closures carry a state. But we got to be very careful with this, though. I want to emphasize closures carry immutable state. It is very dangerous to carry mutable state with closures. Why is this so important to keep in mind? Because Java gives us the capability to do something, but Java makes an assumption. This is what I want to emphasize. In languages like Haskell, where these ideas were really very popular, functional programming languages emphasize purity from the get-go. If you are programming in Haskell, Haskell will not tell you, keep the functions pure. Haskell will follow you home. It'll sit next to you at the dining table and say, I'm watching you. Don't ever have the thought in your mind. And it is there with you when you wake up in the morning. Haskell's sitting there and saying, how's your day going? You don't have such thoughts, do you? This is what Haskell does. It enforces purity every single step you take. Java is like a nice friend. Tells you, you know what, that's not a good thing to do, don't do it. It doesn't haunt you around and say, this is the difference between Haskell and Scala. Haskell will enforce it. Java will assume it. I love languages that assume things. Because when you disagree with the language's assumption, do you know who gets hurt? Not you. Your team gets hurt. Because they are the ones maintaining the code after we are done, isn't it? And this is what makes it really dangerous. Let's look at what this means here, really. When I run this code, notice it ran. Now I'm going to say factor is equal to 2. Notice where I get the compilation error. Line number 16. Java says, are you serious? You're trying to modify this value. Oh, it's final, I cannot change it. Great. But I then remove the word final. This is called effectively final. Effectively final means it's as good as you treated it like it's final. However, if I now say factor equals to 2, notice where you get the error. Java says on line number 13, not on line 16. Java says on line 13, it says, do you realize your lambda is not pure? Please don't do this. Because this is going to result in really bad behavior, and Java is trying to protect you. Well, good news and bad news. Java protected you here, but Java is not going to hunt you down. It's not going to travel with you in the bus and say, you know what you did this afternoon? Don't do it ever again. Java just says it once and walks away. But you know how some programmers are dangerous programmers? They will have a very evil smile on their face, and they will tell you, let me show you how to beat the compiler. Generally stay away from them. Because what they will tell you is this person will have a vicious smile on their face, and they will tell you, look what I can do. And what this person will do right in front of your eyes is the following. They will go to this code and put a square bracket, and they'll pause and laugh. And then they will then say over here, new int, and then they will raise their eyebrow and say, isn't that cool? It's like, no. And then they will put a square bracket 0, and you run the code, notice it still ran. Now they go back here and say, factor 0 equal to 2, and notice Java did not complain. But don't think that Java didn't complain. Oh, somebody's taking a photo. I'll just put a word. Please don't do this. This is the world we live in. You put out code, somebody tweets, and everybody says, this guy is stupid. Well, so now take a photo, please. So the point really is, don't do this. Why? Well, the reason is, what is going to happen when I run the code? I want you to know one thing. Don't think that Java doesn't care. Java is in a state of panic right now. If you closely watch Java C, it is shaking. It is thinking, who are your parents? How did they create you to be like this? Because this is absolutely pathetic way of coding. Why? Because when you run the code, how many of you think the result is going to be 2, 4, and 6? A few of us. Who thinks it's going to be all zeros? A few of us. Honestly, who thinks I have no clue? Absolutely, that's the whole point. I use this question as an interview question. And I pose this question and ask the developer, what's the answer? The minute they try to answer, I tell them you're fired. Because the right answer is, are you all stupid to write code like this? You're hired. Because I want people to write production code, I don't want Java puzzlers on my project. So this is evil programming. We should never do this, because when you run the code, it is lazy evaluation kicking in. Lazy evaluation doesn't come and ask you, do you want me now? It is there all the time. If we are not aware of laziness, we get hurt in the project. I get emails every week from developers. Their email always starts with, the code worked fine until yesterday. I don't even read any further. I go directly to mutability and say, there's your problem. And that's one of the things we have to be very careful. Lambdas have to be pure. In this case, the lambda is not pure. Well, once we honor purity, let's go one step further. What can we benefit from it? Laziness is beautiful, laziness is efficient, but laziness gives us one more avenue of design, which is powerful. And that is, let me give you one last example. And that is, I want to say in this case, given n and k, whatever those things are, I'm going to say find the total of square root of, let's say total of square root of what? Prime numbers. Of k prime numbers, starting with n. So how do I do this? So in this case, I'm going to just output compute n comma k. What is n and k? Let's say int n is equal to some arbitrary number, 101. Let's say int k is equal to, let's say 68, some value, right? So I'm going to write the compute method. So public static double compute. And what am I going to take n and k as the two values right here? Now that we have these two values, what am I going to do? Let's just return a 0 just to make sure the compiler is happy. Yes. So then int index is equal to n. What do we do next? Int count is equal to 0. And then we say double result is equal to 0. Return the result when we are done. Well, that's a good start, isn't it? But then what do we do? Then you say, while count is less than k. At this point, you come to a screeching halt and ask the question, is it less than or equal to? Do you ever ask that question? Every single day. The only purpose of less than in our industry is to make us feel stupid. Because you look at it and say, I'm not sure. Is it less than or equal to? And then what do? Then you say if. In this case, you say, is prime of the value, which is n, or index rather. If it is true, what do you then do? Then you say the result plus equal to math.square root of that number, which is index. But then what do? You have to increment the index, isn't it? So index plus plus. Then what do? Count plus plus. While you're looking at it, let me write the is prime method. So public static, a boolean. What do we do here? Is prime says, given a number n, I want to say return n is greater than 1 and tell me that int stream dot range from 2 to the number, and I'm going to say dot none match given the index I, n mod I is equal to 0. Now, you probably looked at this and said, Venkat, you're wrong. Why is that? Because the index plus plus has to be out. Well, okay, I move it here. Then you say, no, this has to be in, that has to be out. How do you feel about that? That's a lot of complexity in the code, isn't it? But when I run the code, it produces some result. But that's an example of a very accidental complexity in the code, pretty intense, isn't it? But it doesn't have to be that way. Let's give it a try again. This time I'm going to use laziness, but notice what I'll do here. Return stream.iterate. And stream.iterate from where? From n, e plus 1. Just stare at this for a minute. That is an infinite stream. It starts with 1 and keeps on going. 1, 2, 3, n plus 1, n plus 2, n plus 3, n plus 4. There's no end to it. I know what you're thinking. Oh my gosh, if it's infinite, where do you store it? On the cloud, of course. But then, of course, I want to then run through this and I say dot filter. Then I say, given an element, sample is prime. Then I say dot map. And what am I going to do? Map to double. So in this case, map to double. And then I'm going to say, this is going to be math, and this is going to be the square root method. And then finally, dot limit. Limit what? Limit this to k values. Not k minus 1, not k plus 1, not less than or equal to, and then sum, and perform the sum operation on it. Now, if you notice, this hinges on the fact that we have lazy evaluation. How so? Because that lambda is executed on demand. It doesn't execute all the time, otherwise it would just never end. But it runs only as many times as needed. Laziness makes it possible to not only have efficiency, laziness gives the ability for us to have algorithms that can have infinite streams as well, which is a pretty powerful concept. So what I'm really going to with this is, to me, the real important part of functional programming is not immutability. It's not higher order functions. To me, the most important part of functional programming is the lazy evaluation. And without it, I don't think we'll be here talking about Java, because Java does have laziness, and to me, that's one of the biggest, most important achievements in the language, I think, is the fact that they embraced laziness of functional programming, because that gives us efficiency. Hope that was useful. Thank you.